In this problem, we have an insulating sphere. It has a radius A, so this is the sphere, and net charge Q, which is uniformly distributed throughout the volume. Concentric with this sphere is an uncharged conducting shell, so this is a conductor, it has no total charge, and that has an inner and outer radius of B and C, respectively. We're asked to plot the electric field as a function of distance from the center of the insulator, so from here on out to infinity. So what we'll have to do is we'll have to find an expression for electric field everywhere, and then we'll make a plot of that electric field. So let's start with inside the insulator. Which means we're thinking about some distance r less than the radius of the insulating sphere. What is the electric field there? We'll start with Gauss's law. The net electric flux through some Gaussian surface is the integral of E dot dA, and that's equal to the charge enclosed by the Gaussian surface divided by the constant epsilon naught. So next we should decide what is our Gaussian surface. Let's draw the sphere. It has radius A. Our Gaussian surface, since we want the electric field inside, let's pick a sphere that's inside. So our Gaussian surface is a sphere with a radius r which is less than this radius A. To start evaluating our answer, we'll need to sort out what is the integral of E dot dA. That's a result we're going to use in every single part, so let's do that in general first. Once that's done, we'll be able to come back to it. So if we have spherical symmetry, then the integral of E dot dA is equal to the integral of E times dA times cosine of the angle between them. Our electric field points radially outwards, and if we look at a little bit of area on that sphere, that also points radially outwards. So the angle between those two things is 0. So that's the integral of E times dA. For a constant value of r, we'll have a constant value of electric field, so E can come outside our integral. dA, the integral of dA is just A. That's the area of our Gaussian surface. Area of our Gaussian surface is the area of this sphere, which is E times 4 pi r squared. Okay, so we'll use this result for this integral in all of the following steps in the problem as well. So there's the left-hand side of the problem. What about the right-hand side? What is the Q in? Q in means the charge enclosed by the Gaussian surface. If we want to find that, we know that the charge enclosed would be the charge density rho times the volume of the Gaussian surface. So what is the charge density? The charge density would be the net charge Q, so the total charge on the sphere, divided by the total volume of the sphere. So Q divided by 4/3 times pi times A cubed. So our charge density is our total charge divided by our total volume. To find the amount of charge in this Gaussian sphere, we take our charge density and multiply it by the volume of this sphere, 4/3 pi r cubed. So that gives us a charge of, our 4/3 pi cancel, so it's the net charge times r cubed over A cubed. So the charge inside the sphere is a fraction of the total charge. Let's put these two expressions together. Let's put this in for our integral, put this in for our Q inside, and see what we get. So E times 4 pi r squared equals Q r cubed A cubed over epsilon naught. Let's solve that for E. E is equal to 1 over 4 pi epsilon naught times Q times r cubed for A cubed times r squared. One more step to simplify. If you wish, you can write this as Coulomb's constant K. We have r cubed on top, r squared on the bottom. Those divide through to leave us with an r in the numerator times A cubed. There's our electric field inside the insulator everywhere. We might notice that this is going to give us a linear shape, so the first part of our graph we're going to expect to be linear. In the next part, we'll figure out what is the electric field in this white space, in the area, the empty area between the insulator and the conductor.